Our next topic is the fundamental counting principle. So the fundamental counting principle says if there are m ways to choose a first item and n ways to choose a second item, there are mn ways to choose all the items. And a tree diagram is a method of showing all possible combinations of a set of items. And I'm not going to do it in this video, but at the bottom it's going to say open your book to page 468 to discuss tree diagrams. If you go to page 468 and take a look, you will see what a tree diagram is. I'm not going to ask you to create tree diagrams. So that's why I kind of let you look at that on your own. I'm not going to spend time on it. So a computer randomly generates a 5-character password of 2 letters followed by 3 digits. All passwords are equally likely. Find the total number of possible passwords. Okay, so we do 2 letters first. There are 26 letters. So for the first option, you have 26 letters. For the second option, you have 26 letters. The last 3 things are digits. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there are 10 of them. So you've got 10 digits to choose from for the third, the fourth, and the fifth position. So to figure out the total number of possible passwords, we just have to do all this multiplication. 26 times 26 times 10 times 10 times 10. And that is 676,000. Nice big number. Now that we know that, we're going to be asked to do some probability work. We're asked to find the probability of being assigned the password MQ836. Well, that is one unique password. There are 676,000 total possible passwords. So the probability of getting that one password is 1 in 676,000. Definitely leaving this in its fraction form. Now we're asked to find the probability that there's no A in the password. And this takes a little bit more thinking. So, in order to handle this, with no A in the password, what we have to first figure out is how many of the passwords would not have A in them. So to do that, we would have to say, okay, well, there's only 25 possibilities for the letters now, because you're not allowed to have A. There are still 10 possibilities for the digit portions. So because we're not allowed to have A now, I only have 25 options for my letters. So when I multiply all that out, I'll get 625,000. So there are 625,000 passwords that don't have an A in them. So the probability of getting one of those is the 625,000 divided by the 676,000. Yes, you need to simplify this. The lucky thing is it only simplifies by knocking off all the zeros. It is 625 out of 676. Probability that there's exactly 1 4. Well, so there are 3 spots for numbers. The probability that one of them is a 4. Okay. So there are 26 possibilities for the letters. So that hasn't changed. If the 4 is in the first position for the numbers, then there's only one number to choose from, the 4. And we're only allowed to have 1 4. So I'm putting 9s instead of 10s because I can't have 4 in those spots. And that is 26 times 26 times 1 times 9 times 9. That's 54,756. But the 4 doesn't have to be in that first spot. It could be in the second spot, which would shift the 9s around. That's another 54,756 passwords that have 1 4 in them. Of course, the 4 could be in the last position as well. So there's another 54,756 passwords. There are 54,756 passwords that have 4 in the first number position. There are 54,756 passwords that have 4 in the second position. And there are 54,756 passwords that have 4 in the third position that have no other 4s in them. So this is all the possible combinations that have 4, just 1 4. So if I add those up, there's actually 164,268 combinations that have 1 4 in them. So the probability of getting exactly 1 4 is 164,268 divided by 676,000. Now, I'm going to put this into my calculator as a fraction. I am expecting it's going to spit a decimal out at me. Oh, it doesn't. It actually does kind of simplify neatly. It's 243 over 1,000. Cool. If you do this with division, you would get 0.243. So you would give me 24.3%. It's the same number. Like I've said several times, fractions, decimals, percents, I don't care. I will take it in any form you want to give it to me.